Hey guys, this is Ashwin here. In this video, we are going to see another one of the basic projects for machine learning. So that is credit card fraud detection. So this is one of the classification problem we can able to do. So this is also similar to Titanic dataset analysis and Iris dataset analysis. So both are classification problems but with different attributes. So here we are completely gonna deal with numbers, and we also have like new kind of data. So we have to use different scoring metrics in order to calculate the performance of the model. Apart from that, we will explore some new techniques with the help of this data set. Now let's dive into the project. So first we will explore the dataset information. The dataset contains transactions made by credit cards in September 2013 by European cardholders. This dataset presents transactions that occurred in 2 days, where we have 492 frauds out of 284,000 transactions. So that is a lot of transactions, but the frauds, that is so less. So definitely the class labels are completely unbalanced. So we have like few of the negative class and majority of them are positive class. So I will come back to that later. So the data set is highly unbalanced. The positive class frauds account for 0.172% of all transactions. So here we are considering the frauds as the positive class, and it's accounting for only 0.17%. So that's not even equal to 1%. So that is way more less. If we directly do the training without doing much of the pre-processing, means the result will be mostly biased to the positive transactions. Positive means that is non-fraudulent transactions. That's why we have to do few techniques here. It only contains numerical input variables which are the result of PCA transformation. Unfortunately, due to confidentiality issues, we cannot provide the original features and more background information about the data. Features V1, V2 until V28 are the principal components obtained with PCA. The only features which have not been transformed with PCA are time and amount. Feature time contains the seconds elapsed between each transaction and the first transaction in the dataset. The feature amount is the transaction amount. This feature can be used for example, dependent cost sensitive learning. Feature class is the response variable, and it takes value in 1 in case of fraud and 0 otherwise. So 0 is non-fraud, 1 is fraud. So like that the class variable is there, and we can also use the feature for this V1 to V28. So these are all completely numbers. That means the data is compressed, like from so many columns they have been reduced to 28 columns. That's why the PCA is there, and it's not also supporting to the original information, but with the help of PCA we can able to retain most of the information. And I also used PCA in some of the projects, so it is a very helpful module in order to reduce the number of columns we have for training and to reduce the model training time. So given the class imbalance ratio, we recommend measuring the accuracy using the area under the precision recall curve. Confusion matrix accuracy is not meaningful for unbalanced classification. So here they are mentioning accuracy is not like a good metric to use. So they are suggesting to use precision recall or F1 score, area under curve. So like that we can use, and this is like a combination of area under curve and precision and recall. This is also there. I am going to go for a complete classification report, so we can able to see all the precision recall, F1 score, all of them we can able to see. So that's the objective for us, and we will start doing it. First we have the modules. We will import all the basic modules we need. So first import pandas as PD, import numpy as NP. So these are like common modules, and for visualization I'm going to use Seaborn and matplotlib dot plyplot as plot, and apart from that I'm going to import warnings too, and for the warnings we have to set it. So warnings dot filter warnings. So that will be ignore, and matplotlib inline, and these are the basic things we will do for all the projects. Let's run this, and after that we will be going to load the dataset. Now for loading the dataset, we'll be using df equals pd.read csv, and I'm going to mention the dataset name, so that is creditcard.csv. The dataset size is around 150 megabytes, so you can download it from Kaggle or using some other website. Now df.head, let's see the top 5 rows. Now we have got, so here we have a time attribute that is in terms of minutes or seconds, so it can be a timestamp. We will just make it as it is, and all the attributes from v1 to v28, you can see all of them in the range of like minute numbers. It is in the range of -2 to +2. So these columns are the result of PCA. So we have reduced the number of dimensions using PCA, and this is the amount they have spent, and the data set is collected from European card holders. So this is in terms of euro, and the class variables we have. Class is 0 means non-fraudulent, 1 means fraudulent. So that's like a little overview about the data set. Now let's display some statistical information. So statistical info. Now df.describe, and again it will show a lot of information because all the columns are numeric, and we can see here the total number of rows is 2,84,000, and here the timestamp is also there, 1,72,000. So this is like a timestamp, it's not corresponding to the actual time. Have it like a number of seconds, and these are some common variables. You can see the range here, the minimum and maximum range, and it is in the numerical range. The range will be like much smaller, and if we go to all the way to the last, we have amount. So here we have the minimum amount is 0, and the maximum amount spent is 25,000 euros. So that is a lot. And the class, we have only 2 classes, that is 0 and 1. So that's it. And based on the count, you can see there are no null values, so that will save our time for the pre-processing. Let's also display the data type info. Data type info, df.info. Now it will display all the count with data type value. Now as you can able to see, we have like 31 attributes. One is the output, and the remaining 30 are input. So only the output is in terms of integer, and apart from that everything is float. Now that's the brief overview of the data set. Now for the pre-processing, we will just check whether the data has null values or not, and as usual you can see based on the count itself there are no null values. Just in case, we will check for null values. So that will be df dot is null dot sum. So this is a function. Now as you can able to see, there are no null values, and apart from this we do have a lot of columns. So we have the time attribute, and also we have the amount. So except these time and amount column, all the values are in the reasonable range, that is in the minor difference only they are having in the range, but this difference is large, 0 to 25,000, and here 0 to 1,72,000. So we have to do some transformations for these two columns. We can do log transformation, or we can also do standard scalar. So both are applicable. But before that, I will go for exploratory data analysis, and in the end I will try to do the transformation for both of these columns so we can able to easily compare it. Now let's go for a basic exploratory data analysis. First, let's explore the class, that is a categorical column, sns dot count plot df of class. Let's run this. Now you can clearly see the fraudulent class is like very low. You can just see the color, like it's just a single line, because the other class have like so many number of samples. We definitely have to balance the data, or else we will clearly won't have reasonable results. So I will show the difference between balanced and unbalanced class results. So we will keep it there. And apart from this, we have to display all the ranges for these columns. So before that, I will go for time and amount, or we can go for all the columns, and after that we will process time and amount because we have to do some pre-processing there. So to display all the columns, like we have 28 PCA columns, so I'm going to use a loop for that. Now I will have a temporary data frame, so I'll call it as temp. Now df dot drop columns, I'm going to drop time, amount, and the class column. So I'm going to drop these three. So we have like 28 columns. Let's specify the axis equals 1. So we will have the data. Now we will go for the plot. So create plots, that is this plots. Now I'm going to set the figure comma axis equals, I'm just creating subplots so we can able to view it in single go instead of displaying all the things. So we have 28 different columns, right? So we can have 4 columns and 7 rows. So like that we can have, so n calls equals 4, n rows equals 7. We can view it easily. And the figure size equals, I'm going to go for 20 and 10. If the size is not much better, means we can change the values later. Now we need to have the index to iterate through the columns. So initially it will be 0. Now axis equals axis dot flatten. Now we will iterate the data frame, that is this temporary data frame. I'll call it as df underscore temp, so that will be easier. Now for column in df temp dot columns, I'm just iterating through the columns, sns dot dist plot. So specify the column, that is df underscore temp of column comma axis equals axis of index, and we have to iterate the index, so that will be index plus equals 1. So it will be iterating through this index, and finally we will plot it. Plot dot tight layout, padding we can have 0.5, width and height we can also have, so wpad, close it, and wpad equals 0.5, and hpad This can be 5. Let's run this once. Okay, now we are having some error. End row. Okay, this is having yes, end rows. So currently it's trying to display the graph. Okay, now it's like so much compressed. I think we have to increase this to 40 maybe, as we are having so many rows. That's why we are having like a compressed graph. Okay, I think we can have 20 here and 50 here. Okay, that's much better. Okay, now you can see all the columns very clearly, and it's in like different ranges, and most of them are having the bell curve, that is the uniform distribution. So we don't have to worry about like processing these attributes. But you can also pass these data into like standard scalar. That is a common operation if you are dealing with basic algorithmic modules like logistic regression. So when you are subjecting to that, means try to have a standard scalar and after that pass it. I am planning to go for both, like for the basic algorithm to the complex one. So I skip those parts. Now this is done. After that we will explore the time and the amount. Now sns.displot will go for df of time. Now the time is like pretty messy. The difference are like so much huge. We definitely have to transform this column. Let's also go for the amount. sns.displot df of amount. Now the amount is also having like uneven distribution. This is like most of the items are in like $100 or $200. That's why we are having a small curve here, and some of the other amounts are ranging throughout the graph. So we definitely have to use some transformation here, or else you can pass the whole data to the standard scalar and simply process it. So we can go either way. So for this example, I'm going to go for a standard scalar instead of log transformation. So that will be much easier and straightforward. Like if you want a baseline model, means that is a quick way to do. Before that, we can also go for the correlation matrix. So correlation matrix is not much important here because we don't have much meaningful information throughout the columns. All the columns are some random information that are dimensionally reduced using a PCA. Still, we will just explore it once. So correlation equals df of correlation. Now plot.figure. I really need to have a bigger plot for this because we have so many columns. I'm going to have it 20 and 40 maybe, and sns.heatmap correlation anot equals true to display the numbers, and cmap I usually use cool warm, so you can use other color map if you want. Now it should display the graph. Okay, still the graph is like messier, and as you can able to see, we can see some correlation with respect to amount. So that's always like related to these transaction. You can also consider this v28 v27 as like a, from the transaction data they would have arrived to this. So that is meaningful. As you can able to see, class having impact to all these things, like at least a minor impact, and these columns so not having that much impact. and here amount also having correlation to these columns. So these columns are capturing some information related to the transaction, and these columns also having some information related to transaction. Apart from that, I'm not seeing any that much helpful. So I think here we do see some correlation that is corresponding to the time, and V3 have some negative correlation. So these are some inference I can able to get to. I think I have to increase the column size. Now it's good, but all the numbers are like pretty small. I can't able to see it much clearly. So yeah, for the correlation matrix, we usually use to drop some columns. For now, we are not going to do anything. So that's fine for us. Let's scale the whole input now before the input split. Standard scaling. So for this, I have to import a module from sklearn dot preprocessing import standard scalar. Now sc equals standard scalar. Now I'm going to use standard scaling for the input attributes. So I guess we have to do the input split before that. Let's keep it down. Okay, let's do the input split. So for the inputs, I'm going to have drop the output column, so that will be much easier. Columns equals class, I'm going to drop, and access equals 1. And for the output column, I'm going to have y equals df of class. Run this. So all the input attributes are stored in x, y having the output class. Now we can do the transformation. Now I will call it as x underscore scalar. I will use small x itself. Scalar equals sc dot fit transform the input. Let's run this. Now it's done. Let's see what are the values we are having. Now you can see an array with scaled values. So all of them are having pretty small numbers compared to before. Let's see the last one. So these are the 30 input attributes. Pretty small numbers. It's in the range of around -2 to +2. So that's how the standard scalar works. You can see the formula in the internet if you want. Now I think we can proceed with this difference. And here also it's in terms of the array. We lost the data frame, currently x in the form of data frame, but we don't need that now. Let's go for the model training. So I already mentioned the class is so much unbalanced. We will see for the two models and see what is the result. So I'm not going to define a function as usual, but we will just directly jump into the model. Before that, we will split the data. So train test split. So that will be from sklearn dot model selection import train test split. Now x train comma x test, y train comma y test equals train test split. Now we can pass the x scalar Okay, scalar, and y, that remains the same. I'm going to have a test size of 25%, so 0.25, and I'm going to have the random state equals 42. And also, because the class is not at all balanced, we can randomly select the data. We have to uniformly distribute the class variables at least. To do that, I'm going to use stratify equals y. So that is the output class. Now splitting of data is completed. Now let's go for the model training. I'm going to use two models only. One is logistic regression and the other one is random forest for this case. So you can easily replace with some other model name if you want to try different models. So from sklearn dot linear model, import logistic regression. Now model equals logistic regression, and then model dot fit xtrain comma ytrain. Now we also need a scoring metric for the classification report. So before that, I will use y prediction equals model dot predict. So this is for training and testing. I will comment it. So this is training and this is testing. Model dot predict of x test. So the prediction is also done. Now we have to show the result. We have to import classification report. So I guess we have to import another module. Maybe I'll just import it here itself. From sklearn dot metrics import classification report. Now classification report. Okay, I have to run this again. Now classification report of actual values, that is y test, predicted values y pred. Run this. Now it's gonna train and test it. So I have to print this in order to see the results properly. Print, run this. Okay, now you can see the classification score. So we have two class variables, 0 and 1. Support means that all the samples we are taken for testing. So if you see the accuracy, it's 100% for logistic regression itself. I think because of this standard scalar. But we cannot go for the accuracy as majority of them are going for the non-fraudulent samples, like majority of them are non-fraudulent samples. And here also you can see the precision recall and F1 score is all 1%, and in the precision recall and F1 score we have less values for the main class, that is the fraudulent class. So we are having some misclassification here, and and if we consider the average, so it is 0.86. So that's the thing we can observe using the micro average. So this is the average of this F1 score, and you can also add some more metrics. So F1 score is like a combination of both precision and recall. That's why I'm using this score. And if you print it, print F1 score. Okay, I didn't run it again. Maybe I should have run this separately. So F1 score, again y test comma y prediction. So here the F1 score is around 72. So that's not much reasonable for us. So that's why we have to go for some other approach. So this is the score we are going to consider for the better model. So I'll also display some information like F1 score. So that's pretty neat. F1 score, that should be good. Now let's copy this and use it for another model. I'm going to use ensemble. I'm going to use random forest classifier. Let's run this. So it's taking much time because the dataset have like so much values. That's why. And you can see the count here. Here you can see it's having like 2,84,000 rows. That's why. And random forest is like a complex algorithm. So it will take some time compared to other algorithms. So logistic regression is like a simple formula. That's why I just predicted quickly. So it's taking much time. So I have to enable the parallel jobs. So if you specify the parameter n jobs, it would have been much faster. Okay, now we have the results for the random forest. It's been much better because we are showing some good results. Like compared to 0.72, it's going up to 0.85. All the precision and recall have been improved. And in total, F1 score is also improved to 84. So that's pretty much reasonable. So this is because of unbalanced training. That's why we are getting somewhat low score even with a large amount of data. So in order to overcome this, we will try to balance the class ratio. So we will balance the class in equal distribution and train the model with this two similar models and try to do that again. So for this, I'm just gonna copy and paste it. But before that, we will go for the class imbalancement. Class imbalancement. So this will help to balance the class with equal distribution. Equal distribution. Okay. Now before that, I will show you the ratio of the class. I'm going to use the X train and the Y train for this. That is the scaled attributes we have. So let us display. So SNS.displot Y train. Run this. Okay, currently it's in the, sorry, it's not displot, it's count plot. Okay, now you can see the number of samples for class 1, it's way more less. Let's try to balance it now. For this, I'm going to use a module. So from imblearn dot oversampling, import SMOTE. So this is for oversampling. Instead of increasing the data, we can also reduce this huge amount of data, and you can use the combination like random undersampling and random oversampling. So I'll also comment it. Hint: use combination of oversampling and undersampling. So that will produce some good values for the training. Now let's initiate it. Oversample equals SMOTE of, we have to specify the neighbors, but we will just pass it as it is. Now I will call this as X SMOTE comma Y SMOTE. So we have to pass oversample dot fit transform, or okay, this is here fit resample. I have to pass the input and output, that will be X train comma Y train. So why I am not doing with the whole data means it will also have the duplicate columns for the testing. That's why I'm going in a different approach. Instead of transforming this whole data, I'm just transforming only the train data. So this will give us a good results. Let's run this. Now it has been run. Now let's see the class distribution. Why SMOTE? Now you can see the class number 1 has been increased to so many samples so that we have a equal distribution of both classes. So the model will give weightage for both of these classes. So that will be very much helpful. So let's see whether this technique improving the score or not. I'm going to copy and paste this. So if you want to copy the cells means just press shift and press the arrows, Control C and Control V. Now for the random forest, I am going to have this n jobs equals -1. So it will use all the CPU cores. So it will be much quicker. Let's run the logistic regression. Before that, we are having around 72, and here also you can see the results. Let's have it. So now are we seeing any change? I think the change is like not much. It's having the equal changes only. Okay, I didn't change the training and testing. That's why we are not seeing any. So now let's change the training data. So that will be X SMOTE and Y SMOTE. Let's run this. Now this should take some time. In the meantime, I'll just copy this and paste it here. Now let's run this. Okay, so we have done the SMOTE, and for logistic regression it's not at all giving a best result for us, but for random forest the result is much closer to this previous result instead of doing the class imbalancement. But sometimes because of balancing the class, it will give you a perfect model because it will give weightage for both of these classes. I think due to the complex model, it's actually giving better weightage for both of these things. That's why we are getting 80 around 84 F1 score. And here also with the help of the standard scalar, we are getting around 71. But due to large number of samples, now the logistic regression is not at all predicting correctly. So apart from that, we do have the random forest classifier, and this is giving around 83. So it's not that much of a big difference. Maybe we can use one more model. So we have done a tree model. Let's go for some boosting model. I am going to use XG boost. So that will be from XG boost, import XG B classifier. Okay, now copy and paste this. Let's run this once. This will be much quicker compared to the random forest. So I'll also use the same for the previous for comparison. Let's run this. I have to wait for this one to run and complete it. So now this is also giving like less F1 score, but compared to the macro average, it's in the macro average it's giving 90. Here it's giving 92. So the random forest is the winner here. Let's see the before one. It's also giving the same thing regardless of the. Okay, this is X train and Y train. So here this is giving like 86. I guess for this data we don't need to do the class balancing because after balancing the class, it's not at all giving the best results. I think we have to do a random undersampling and oversampling. Maybe based on that it may change, but we have to do some kind of trial and error in order to balance these things. But here, without doing the class imbalancement or balancing the classes, we are getting a pretty good score with the XGB classifier. We are getting the F1 score of around 86, so that is the best out of all the three models I have used. And here also, using this standard scaling, we are having a good results because of that. And you can also use log transformation for other attributes like time and amount. So that is the other way of doing. And that concludes the whole project. So this is like a easy project. You don't have to like stress hard and do all the manipulations here. Apart from that, you can add some like few techniques and try out hyperparameter tuning and other few techniques in order to increase this F1 score in order to get the better metrics. And that concludes our whole project. So we are having good results. If you consider the accuracy, it's having 100% accuracy here, but it's not 100% because of large amount of values. It's going around 99.9% accuracy. That's why it's rounding it off and showing it as 100. You just see the F1 score. So that is the combination of precision and recall. So higher the score, better the model. So that's how we have to conclude. If you have any more techniques and if you got more score compared to this 86, that is the F1 score, just leave the comment below with what changes you did for your dataset in order to achieve this score. So that will be very helpful for the community, and I will be seeing you guys with the new project.